Welcome to the last section of Chapter 11. Yay! Almost done! Okay, so I'm going a little bit off the packet on this, but not terribly. So you should be able to follow along with your packet. I didn't go like seriously my own way here. So one of the reasons that we looked at electron configurations was to help us understand why different elements, atoms on the periodic table behave the way they do. There's a clue in the electron configurations. The first thing we need to look at are the three main groups of the periodic tables. We talked about this a long time ago. Okay, everything pictured in the green, metals. Got that? Metals. Metals have specific properties that are unique to metals. For example, they're lustrous. And lustrous, by the way, if you need to know this, be a good thing, means they're shiny. You should also know that metals are malleable, and that means you can pound them into sheets. They can be pounded into sheets, kind of like the iron is there. Metals are ductile. That means you can pull them into wires. Copper is very ductile. And they make good conductors, and you should know from Chapter 10 of both heat and electricity. And I'm going to abbreviate electricity. The biggest chemistrian thing about metals that I'm sure you already know is that they form, wait for it, cations. Yeah, cations. And how do they form cations? They lose electrons. I've lost an electron. Are you positive? Oh yeah. So when you lose this electron, booyah, like this one over here, it's gone. The ion is then positive. All metals make cations. Now, there is some debate in the nonmetals community about whether the noble gases are really nonmetals or not. I mean, after all, they're noble gases, and for the most part, they don't play chemistry games. But I've always called them nonmetals and probably still will, even though they don't play chemistry games. And to me, they're a lot more like nonmetals than metals. So, and they're over there on that side of the periodic table. So we're going to go with the whole, yeah, they're nonmetals. Yep. Nonmetals have characteristics that are basically just the opposite of metals for the most part. I mean, carbon as graphite can conduct electricity, but they're not shiny, they're not malleable, they're basically the opposite. If a nonmetal, they don't always do this, but if a nonmetal forms an ion, it forms it by gaining electrons to make it an anion. And it's kind of cool with the word anion, in case you don't remember. The word anion means a negative ion. Yeah, they don't always do this. Because remember, nonmetals have two types of bonding. Do you know what they are? Okay, type 1's ionic, type 2's covalent. And ionic bonding is when they make anions by gaining electrons. I haven't spent much time talking about the metalloids, that funny little staircase here in the middle. Basically, I've said to you, they don't know what they are. They're metals or nonmetals because they contain properties of both. Metalloids, this is a picture of silicon, by the way, and metalloids are solids at room temperature, like metals are for the most part. And metalloids are very brittle and hard. Now, brittle means things can break easily. Now, obviously, this piggy bank is not a metalloid, but it's a good picture of something that would be brittle, breaks easily. Metalloids, like this metal shown here, is brittle. They break very easily. And when they break, they shatter. Metalloids are called semiconductors. And what this means is under certain conditions, they can conduct. Only under certain conditions do they conduct. I think I put that on there. Yep, I did. And this is what makes them excellent for computers. And why does it make them excellent for computers? I'm not that much of a geek to know the answer to that yet. It's on my list. To look at the chemical properties of each of the groups on the periodic table, we need to look at the valence electrons. And to do that, you kind of might need a piece of paper or something else to write on, because I kind of go off the packet here. Everything in column 1 is called an alkali metal. And these guys have one valence electron. If you don't believe me, well, let's take a look at lithium. Lithium has an electron configuration of, okay, you do it. Pause it. Do it. Okay, yeah, I got 1s2 and 2s1. Sodium, and I'm going to use the shorthand configuration. Well, yeah, sodium has, go ahead, you do it. Okay, so sodium has the electron configuration of, and I'm going to do the shorthand version of sodium by neon, and then it becomes 3s1. And potassium, well, that becomes argon, and 4s1. You kind of see the pattern. They all have one valence electron. And that's what makes them all behave essentially the same way. They're very reactive. But look at this. This is a picture of what potassium's doing. Watch cesium. Whoa. So what do you think happens to the reactivity as you move down the periodic table? What's your guess? Let's take a look at group 2. All of the alkali earth metals have 2 valence electrons. If you don't believe me, do the electron configurations. They all have 2. And look, this is how they react with water. This one is beryllium, and then here we have magnesium and calcium and barium. The increase in bubbles means it's more reactive. So as you move down the periodic table, what do you think happens to reactivity? If you said that as you move down the periodic table, metals become more reactive, you got it. So as you move down, it becomes more reactive. And sure enough, francium or francium, tomato, tomato, is the most reactive element on the periodic table. And it is the most reactive metal. And the farther you get, the less reactive it gets. The farther you get, the less metal-like behavior it would have. And of course, we're going to ignore the noble gases. Now, the trend isn't usually drawn on the diagonal, so we say as you go closer to the first column, yeah, that's a fun straight line, the metals become more reactive. And as you move down, they become more reactive. And this guy, big time. I don't worry too much about these guys just because we don't play with them in our labs. So don't worry about it. If you look at atomic size, which actually has something to do with their reactivity, so there's a relationship between atomic size and reactivity, but take a look. As you go down the periodic table, do you remember what we said happened to their metallic-like reactivity? Right. So the reactivity goes up, and look what happens to the size as you go down the periodic table. Yeah, that's a wonderful straight line, isn't it? Yeah, the size gets larger. That should not be a surprise. I mean, after all, lithium only has 3 protons and sodium has 11 and potassium has 19. And yeah, you got to house all those and those electrons and all those orbitals packed in there. I mean, cesium's got 7 layers of s orbitals. It's got p, it's got d, it's got f orbitals stuffed all in cesium. So yeah, this thing's ginormous. But what do you think happens to the atomic size as you go across the periodic table? If you said bigger, you're like everybody else. But look at this. Whoa, it gets smaller. Okay, yeah, that doesn't make any sense at all, is probably what you're thinking. You're like, what's happening? I mean, after all, lithium only has 3 protons. Carbon has 6 protons. Oxygen has 8 protons. Why are they getting smaller? And they're not very metal reactive, are they? To explain why the size of the atoms goes down as you go across the periodic table is what's called the effective nuclear charge. And what this is, it's the relationship between the nucleus and the electrons. See, what's the charge on a nucleus? Well, the nucleus has protons and it has neutrons. What's the charge on a proton? Yeah, you're right, it's positive. And on a neutron, there's no charge. So the nucleus then is positive. And we know the electrons are negative. But it's not an overall charge of 0. There's this thing called shielding, which kind of like hides the nuclear charge from the valence electrons. So within, let's look at the second energy level, we have 2s and 2p orbitals. Lithium has this positive 3 on its nuclear charge. Yet go way over here, neon has a positive 10 on its nuclear charge. The neon's nucleus, what the effective nuclear charge basically means, is because neon has such a bigger nucleus, it's able to pull those electrons in much more tightly and hold on to them, thus decreasing the size of the atom. So the trend is, as you move up the periodic table, they get smaller, or you could have done this as you move down, they get bigger. And as you go this way, the atoms also get smaller. Helium is the littlest guy on the periodic table, even though we don't deal much with him because he doesn't play chemistry games. So after helium, the next, really, the little guy that you should deal with, fluorine. That is the smallest reactive atom on the periodic table. Now, remember down here, this metal was the most reactive metal, and it's also the biggest. And the reason it's so reactive is its effective nuclear charge is so small that those electrons are free to react whenever they want to. Arrange the following atoms in order of decreasing atomic radius. Okay, these kinds of questions tend to throw students, so let me give you a tip on how to answer it. So we want decreasing. That means we're going to go from the largest to smallest. And what I just wrote down is often very helpful for students and for me when I grade your test, because I know what you mean. And if you misinterpret the question and say you write them in terms of increasing atomic radius, then I know that you still know the correct answer because you've given me a clue with the large to the smallest. So let's take a look at the periodic table and identify the location of these atoms. Here's sodium, here's aluminum, and phosphorus, and chlorine, and oh, we've got to put magnesium over here. So the biggest one we have is sodium. And sodium is bigger than magnesium, which is bigger than aluminum, which is bigger than phosphorus, which is bigger than chlorine. And you can use commas if you don't like the greater than sign. As long as I have this as a guide, the commas are fine. Which atom is bigger? Well, we have to look at the periodic table. First A, we're looking at sodium and cesium. Correct answer is cesium. Next, we have, I'm going to change my pen color here. Let's go with green. Beryllium and barium. And the winner is barium. Okay, changing the pen color. Now let's do nitrogen. Oh, there you are. And now we have to do, ooh, what's SB? Well, if you said antimony, give yourself a point. Yay, antimony. Who's bigger? Yep, antimony. Now, let's see, new pen color. Fluorine and bromine. Who's bigger? Yep, bromine. And last but not least, neon versus xenon. And yes, xenon is the correct answer. Ionization energy is an interesting concept if you're a geek like me, but this is the exact definition of it, and not entirely sure why we use the gas phase. One of those things I still need to learn. However, ionization energy is the amount of energy needed to take away an electron, to take one away from it. Do you remember who the most reactive atom was on the periodic table? You're right. If you said francium, you would be spot on. Remember how big the sky is? It so does not care about those outer shell electrons. Those electrons, those valence electrons, are free to leave, go, goodbye. Francium doesn't even care. Because it's so big and has so many electrons, these electrons are easy to remove. But if you look over here, fluorine is a really small atom, and it has a really high effective nuclear charge, and it holds onto its electrons very tightly. It does not let them go. It's like that big mama bear going, no, those kids cannot go, they're mine. And it has a ridiculously high ionization energy. That's right. It is really, 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 really hard to make fluorine a cation. See, metals in general have a low ionization energy because, in order for a metal to become an ion, I've lost an electron. Yeah, I mean, they're pretty easy to give those away. So metals in general have low ionization energy. They're more than happy to remove an electron. Nonmetals, on the other hand, have a really high ionization energy because the definition of ionization energy is to remove an electron. Nonmetals don't want to take one away. Nonmetals want the opposite. They want to gain electrons. So why would they give one away? In order to take one away, you're going to have to put a buttload of energy in there because they're sitting there with their little electrons going, I'm not giving them away. In fact, bring me more electrons. They want them. This is the actual trend. As the atoms get smaller, the effective nuclear charge increases. They hold on to their electrons more tightly, and so the smaller ones are a little more stingy with their electrons. These big fat ones down here, yeah, they're easy. As you get closer and closer to fluorine, the ionization energy goes up. These guys, especially these green ones, they want to hold on to their electrons. They're not interested in losing them. In order to take one away from these guys, you have to spend a whole lot of energy. By the way, fluorine, he's the stingiest on the entire periodic table. I like to think of fluorine as being the seagulls out of Nemo. They sit there and going, mine, mine, those are mine electrons? Yeah, it's really hard to take them away. I like this question a lot. Why is the second ionization energy always greater than the first, no matter what the element is? Well, the answer to this is pretty simply, if you take one away, the effective nuclear charge goes up. And the higher this guy is, the harder it is to take away an electron. So when you remove one electron, the nuclear charge goes up, so therefore it's harder to take away a second. Place the following atoms in order of increasing ionization energy. Now, do you remember who I said was the stingiest one on the periodic table? Yep, fluorine. Closer you are to that guy, the greater the ionization energy. So we've got, not fluorine, so I'm going to change my pen colors. So well, here we go. Yeah, we'll use blue. So I've been given, we do have fluorine. Oxygen, fluorine, sodium, sulfur, and cesium. Increasing, that means to go from small to large. So by small, I mean who's the easiest one to steal an electron from? Cesium is correct. Cesium is easier to take one away from, who's next? Sodium is correct. So cesium has a smaller ionization energy than sodium. Who's next? Sulfur, good. Sulfur's a little bigger. Then we have oxygen, and then we have fluorine. Yeah, he's the toughest one of all. Well, that does it for the chapter. I'm working on doing a PowerPoint for your study guide so that you can get the help you need to cover the study guide. It's in progress, so I'm working on that. Our next chapter will deal with Lewis dot structures and VSEPR. Have a great day.